Good afternoon, everyone. My name is Alexander Chabot-Leclerc. You can call me Alex. I'll know you're talking to me. I will be helped for this tutorial by Glenn here, Glenn Granzo, and Gil Forsyth. First thing I would like to do is a little sort of questionnaire. Who has been using Python for? Who has been using Python? Who has been keep your hand up if you've been using Python for at least a year. Okay. More than 2 years. Okay, cool. Good to see you. Who has used NumPy before? Most people, or you've seen it, sort of. You've seen someone else use NumPy, therefore it's like driving a car. You've seen someone else drive a car, therefore you think you can drive a car. It's not that hard. And then the next thing I want you to do is to introduce yourself to your neighbor, both sides, because Glenn and myself and Gil are going to help you during exercises, but your neighbors are also a great source of help. Yeah, this worked better than I expected, so I'm glad you made some new friends. They'll still be there at the break, after the break, tonight, tomorrow, so cool. So yes, this afternoon we're going to talk about NumPy with just a little sprinkle of matplotlib in there. And there are 1 or 2 exercises where we'll want to look at the data, and we'll use matplotlib for that. So this is not a matplotlib tutorial. I'll teach you just enough matplotlib that you can see things. I assume some of you might have signed up for the matplotlib tutorial, which is tomorrow morning, maybe? Yeah, great. If you have any questions during the tutorial, you're welcome to raise your hand. Don't shout. Well, if I'm looking down, you can just shout, "Hey, Alex!" But raising your hand is probably better. All right. So I thought I would start with a little sort of motivation of why we're using NumPy. So I'm using this application here called Canopy. You can use Spider if you prefer. For this class, that's not a problem. All exercises are in plain Python files, so you can also open them in a text editor and use them in Jupyter. This is a very simple tutorial. There's no Docker file. There's no virtual machine somewhere. It's just Python, NumPy, and us. It's a very cozy thing. So let's say we live in a world where there is no NumPy, and we have some list of numbers. One called A, super exciting. This is a list of 5 numbers, and one called B, which is also a list of 5 numbers. And we want to add those 2 lists together. So we might try to add those 2 lists together, but that doesn't have the intended effect, right? It concatenates the list. So that's not what we want to do. What we want to do is we have to go through pairwise the first element of A with the first element of B, add them together, the second element of A, second element of B, something that looks like for first comma, result equals an empty list, for first, second, in, then there's this function here called zip. It's a little bit like a zipper is going to take our 2 lists, and like a zipper takes the first tooth on each side. This is going to take the first element of A and first element of B, return them. Same thing for the second, third, fourth, etc. So I'm going to do result.append first plus second. And result would look something like this. So you can imagine that these sort of 3 lines of code, they're not super complicated, but they get really annoying if you have to do things over lots of data. Or things with multi-dimensional arrays, in which case we would need to do like 2 layers at least of for loops. So it'd be a lot of typing, and it would also be, in the grand scheme of things, very slow. Slow compared to what your computer can actually do when doing these computations. So that's where NumPy comes in. So throughout this tutorial, whenever you see NP, you should think NumPy. So most people, when they work with NumPy, they will import NumPy under the name NP, so it's a little bit less typing. And then every time they use a NumPy, you use a NumPy functionality, you'll use the NP prefix to say whatever comes after that. If I'm creating an array, for example, np.array, I know that array comes from the NumPy package. So what I'm doing here is I'm creating an array. I can look at the type of this variable here. It's a numpy.nd array. The nd stands for n-dimensional. So we're going to start easy, one-dimensional objects. Then we're going to go to 2D, and we'll talk a little bit about 3 and 4-dimensional arrays. But for this tutorial, we'll mainly stick to 1 and 2D, things that are easy to look at and easier to reason about. So what is special about this array? One thing that is special about this array is that it has something called a D type, which is short for a data type. And what that means is that this array enforces that every object that is put inside of it, every value that is put inside of it is of this type. So int stands for integers, whole numbers, 0, -1, 1, 2, 3, etc. And the 64 is how many bits are used to represent this number. So this is a 64-bit integers. What other types exist? 32-bit integer, yes. Unsigned integers, yes, that exist as well. There are some, you can do that in NumPy. We also have floating point numbers. So I have the array C, let's say, or let's call it F, and p.array 1.2, 2.3, 4.5, 5.6. So this array F here has a D type called float64. So in this case, this array has floating point number, fractional numbers. And what I mean by a constraint about what the data that you put in is if my array A here, if I try to assign to it a new value. So I have my array A. It is a sequence, a little bit like a list, meaning that I can use the square brackets like this to access a value. So I can access a value at a given position. I can also assign. So right now there's a 1. I'm going to put in a 10. So now my 1 has been replaced by a 10. And that's all good because I'm putting an integer in an array of integers. But if I try to assign, instead of a 10, let's do 11.5, then in this case, my sort of the decimal portion of the number has been truncated. So there's a very strong constraint in NumPy that all the data has to be of the same type. A few other attributes that are here. There's also something called ndim, short for the number of dimensions. So I mentioned that we're going to work with 1D and 2D arrays. This array here is one-dimensional. And possibly the most important one, because it's going to drive so much of the behavior, is called the shape. What is this? What does shape return? Tuple or tuple. Yes. So shape is always a tuple that shows the number of elements along each dimensions. So here my array has 4 elements. Therefore I have a tuple of a single element and it's a 4. We're going to see that in 2D this tuple is going to have 2 elements. In 3D it would have 3 elements, etc. Anyone's a convert from MATLAB here? It's okay, I was one of you one day. So shape is equivalent to size in MATLAB. There is also an attribute called size, which is a little bit confusing, which is an integer, always, that only represents the number of elements in the array. Not the shape of the array, but just the total number of elements. All right, let me go back to my notes here. All right. So what can we do with these arrays? So I have my array A, I have an array F. I can add them together. Right? And unlike with my lists, what happens here is that I get element-wise operations. All my values get added together element-wise. I can multiply one by the other. I can divide one by the other. I can even raise one to the power of the other. And everything is done element-wise. So these are not matrices, they're not vectors, they're really arrays of elements. And what NumPy does is that it treats them element-wise over the entire array. This kind of operation here, where you multiply or do some operation between two arrays and you're not writing a for loop, but there's sort of conceptually a for loop happening somewhere, is called a vectorized operation. It's a word that you might have heard about. When you think vectorized operation is how to write a single statement without a for loop that explains sort of a looping concept. These vectorized operations, they can be done between arrays, but they can also be done between an array and a constant. So remember, my array A is integers. I can multiply it by 10. Right? And every single element in the array will be multiplied by 10. So this functionality, the vectorization, the data structures, they're two of the things that NumPy bring to the table. And the other thing that NumPy brings to the table is a set of tools. They're called universal functions, commonly called ufuncs. It'd be funner if there was ufunc with a K, but it's with a C because it's short for function, not for func. And what those are, they're mathematical functions. So the plus is sort of, in a way, a universal function as well. But they're mathematical functions that are optimized to be applied onto NumPy arrays element-wise like this. So sign of A, for example, goes through and computes the sign value of every single element of A. Let me use the slides for this next section here that I briefly covered already. If you're following along on the GitHub repo, there's a PDF of the slides that I'm using. I'll be doing a mix of using the slides for some things because I think it's nice to see the before and after that don't move. But also sometimes doing, I call that code karaoke. It's like type along thing where I'm going to be typing something and you're welcome to follow along on your own computer. So what we're illustrating here is how NumPy arrays are both sequences, like lists, in the sense of you can get elements at a given position using this square brackets notation. But also like lists, they're mutable sequences, meaning that you can assign to a position in the array to override the data that's in there. And what we're showing on the right-hand side here is what I was showing just earlier, this enforcement of the D type, the data type, where the array will not let you put in some data that has been, that is of a different type. So in this case, our integer array, if we try to put in a float, that gets truncated. If we had a float array and put in an integer, it would be upcasted to be a floating point number. All right, so let's now look at what happens if we go into higher dimensions. We go into 2D. What I'm creating here, sort of by typing it by hand, is a two-dimensional array. That if I just type A, if I just type the variable name, IPython will show me nicely, not IPython, but NumPy will show me nicely aligned, so all the columns align together, all the rows are together. And conceptually, what you can think of your array as is kind of, not exactly, but kind of a list of lists. So if you have a single list, it's like a one-dimensional array. If you have a list of lists, it's a two-dimensional array. If you have a list of lists, 3D array, etc. So this particular array here that we're working with, if you look at its shape, it's a 2x4. So the outermost list has inside of it two lists, right? So that's the first element of the shape. And then each of the inner lists has 4 elements. The size, that's the total number of the elements, is basically the product of the shape. In this case, we have 8 of them. Ndim, which is you can think of it as the length of the shape, is 2, right? We have 2 dimensions. And our two-dimensional array, just like our 1D, we can access elements inside of it and we can set elements inside of it. But a little distinction compared to what we do with lists is that we can put our coordinates in the same set of square brackets. Right? I think of them as like, yeah, coordinates into this two-dimensional objects. So the way to read this here, the first one is the row, because again, Python uses zero-based indexing. That's row 1 is the second row, and then row 3 is the fourth column, so that's the lower right here. So at first, the lower right contains a 13, and then we go in and we override a value at that position. So same concepts in 1D, in 2D, in 5D. Your arrays are sequences. They can be indexed. And you can use this notation to set also a value. And in cases where you don't specify as many indices as you have dimensions, so in this case, A is 2D. If you specify only a single index, what you get is everything from that element or that dimension down. So A1, you can think of it as, if I look in the upper left here, my NumPy array is the outermost container is made of 2 lists. Therefore, A1 gives me all of the inner lists, the 10, 11, 12, 13. If you're coming from MATLAB, this is a little bit different, where MATLAB would give you just element number 1. Any questions so far? Anything surprising? Okay. The question is how to grab just a column is the next step. We're going to get there in just a second, as can be hinted by this illustration here. So yeah, what I showed here, this concept is called indexing, and it's designed to pick, in most cases, only a single value. So they're really coordinates of a point in your array. Our next topic is how do we bring that to select more than one point? How to select an entire row, an entire column, every other element of a row, every other element of a column, etc. So this concept is called slicing. And if you've used slicing in sort of pure Python with lists, this will feel very comfortable because it works exactly the same way. So the syntax for slicing still uses square brackets, but involves at least 1 colon, sometimes 2 colons. And the idea is the first value before the first column, sorry, this is so hard. The first value before the first colon is the lower bound, is where to start. Then after the first colon is the upper bound, where to end. And then there's an optional third step or third value after the second column, which is the step size or the stride size, which is how many elements to jump over. So we have a few examples here, and we're slicing inside of this list here of integers. So this first slice, A1 colon 3, means from element number 1, which is the second one, to element number 3. And just like in pure Python, the upper bound is never included. So the way to think of this in mathematical term is that it's a closed interval on the left and an open interval on the right-hand side. Then what we're demonstrating after that is the possibility to specify positions using negative numbers. So positive numbers are from the sort of the left-hand side of the array. 0 is the first one, 1 is the second, 2 is the third, etc. But Python does not include an extra keyword to represent the end of the array. There's no end keyword, for example. So the way it works is that it uses negative numbers. So -1 is always the last element of your sequence. So that allows you to do things like from 1 to colon -2, which ends up in this case making exactly the same slice. However, I read these two things entirely differently. The 1 colon 3, both of them are relative to the beginning of the array. And I look at that and I am guaranteed to see a slice of 2 elements. Right? I do 3 minus 1 in my head, that's 2, I'm going to get a slice of 2 elements. Whereas when I see a positive number on the left-hand side and a negative number on the right-hand side, what I think here is I'm going to throw away the first element, and I'm going to throw away the last two elements. Right? Those are relative to the edges, the left edge and the right edge, or the first row and the last row. So here, when I see this, I don't know necessarily ahead of time how much data I'm going to get out of this. Here, I can know because right next to it I have a small array of 5 elements. But in larger sort of data manipulation tasks, if with images or something like this, the only thing that I know here is that I'm going to make my image, or I'm going to make my array a little bit smaller by 1 element on one side and 2 elements on the other side. And that last one here, although it is possible, I think is absolutely insane, because this ends up making the same selection in this small array, but it's really hard for my little brain to predict what's going to happen here. It's possible that like if you're doing this weird like circular indexing pattern that you end up with positive and negative indices, but this just breaks my brain, so I assume it breaks other people's brain too. So be kind and don't do that. Then on the right-hand side, we have a set of really common use cases, which is to omit a bound. So either to omit the lower bound, to omit the upper bound. And the way I read these two are a way of selecting either the head or the tail, if you're a Unix user, of some data. So the way to read :3 means from the beginning, which will be 0, to 3, the upper bound is not included. So I see this number here and I find it wonderful. I see the number 3, I know I'm going to get 3 elements. Similarly for -2:, the way I read this is I'm going to start 2 elements from the end, and I'm going to go all the way to the end. And I know, I see this -2, I know I'm going to get exactly 2 elements out of this. So super useful in NumPy or even in Pandas if you want to look at like the first few rows of a data frame, or the first few last rows, or some columns, or you have lots of data and you just want to see a subset of it. Those are super, super useful. And finally, we have an example here of just specifying some colons and omitting both the lower bound and the upper bound. And the way to read this is go from the beginning to the end. So basically all the data along that dimension, but picking only every other element. So that's kind of downsampling so that you pick every other element only. We still haven't gotten to that lady's question, which is how do we get a column? And now's the time. So we have a few examples here of applying sizing in multiple dimensions. Our first one in yellow is a mix of both indexing and slicing. So first we index along the first row. That gives us row 0 and 3 to 5. So that's column 3 to 5. The upper bound is not included. So that gives us a slice of 2 elements. Then in light blue, we have 4:4:. And I see this, what I think is I care about the lower right portion of this array or this image or something like that. I'm going to throw away 4 rows and I'm going to throw away 4 columns. In this case, that ends up making this 2x2 selection here in the lower right. And we finally get to the column selection. And this is where we see this probably for the first time, a lonely colon. The lonely colon means everything along that dimension. So that in this case, that means everything along the first dimension, everything along the rows. So all the rows of column number 2. And there's a funky thing that's happening here is that when we make this selection, what comes out is a one-dimensional array. It is not a column. It's a 1D array, which is conceptually in NumPy a row. So that's just how it is. So if you're indexing into an array, you end up dropping a dimension. So here we start in 2D. The slice gives us every element along that dimension. And the index because we want only one element along that dimension, we end up dropping one. And finally, at the bottom here, a mix of example of strides. So we start from row 2 until the end, every other. So these are these black sort of edged cells. So we pick every other cell, but with an offset from the beginning. And then along the other dimension, along the columns, we start from the beginning to the end in steps of 2. I'm going to put this up here. There's a little bit of starting code to create this array. So this function here, np.arange, not np.arrange, that is different. Arange creates an array of 25 numbers, just like one long array, and then reshape makes it square, makes it rectangular. And then I want you to make these 3 slices. In yellow, there's a slice of the last row of the array. In red, we have 2 columns. And then we have this sort of patchwork, this grid of elements with light blue squares that do not include the last column. So we're going to take 5 minutes or so to work on this exercise. Let's start with the red selection. So red is a slice of A. Is it a 1D slice or a 2D slice? 2D slice. I'm not going to put the red just yet. So if I know it's 2D, I know I'm going to need a comma in there. So that's a little bit how I build my slices. I know I'm going to need a comma. What comes before the comma? Is it my row-wise selection or is it my column-wise selection? Row-wise. So in this case, what's the concept, what's the idea that I want to capture for doing the red? All rows. Yep. And how do I write that concept of all rows? The lonely colon. Yes, that's not the technical term. Then I want some column selection. And there's a step here. There's some step size. So I know I need at least 2 colons. And I might not be sure yet what my offset should be, but I know that I want to skip at least 1 column. So I know that my step size is going to be a 2 like this. So I might try this. Oops. Try to run this. Okay, this does select every other column, but it's starting from the beginning, right? I have a 0, the 2, and the 4. 0, 2, and 4, and that's not what I want. I want that selection, but shifted by 1. And that means that my starting index, my column offset should be a 1. So that means start from this column here all the way to the end in steps of 2. So that's what I'm looking for red. Colon, comma, 1, colon, 2. So that is red. I'm going to put that up there. Let's do yellow. So what do I want to do with the rows? Just 1 row. Which one? Yep. 4 is good. And what do I want to do with the columns? All of them, right? So this works fine, right? That row number 4, all of the other elements along the other dimension. There was an example that we've seen earlier where if I want everything sort of below that dimension, I can omit the trailing colon here. If I do 4, it'll be all of the elements in the 4th row. Upsides and downsides. Here, even though it's not required, it has the benefit of telling my future self or my colleagues or whoever is going to read my code that this array here has at least 2 dimensions. So that has some value. And it will also fail if for some reason like this array here is 1D. This code will succeed, but might make your code fail somewhere else. Whereas if you explicitly ask for a slice over 2D, if that array at some point is 1D, this will fail right there. So the sooner it crashes close to where the cause of the error is, the easier it will be to debug. So being explicit is worth it, in this case at least. Anyone else tried something else in this for this sensor?
You could formally assign it as the last row, not row 4, but the last row.
And how do you express this concept of last row? Yes, -1.
And again, I recognize that those are identical in these examples, but you were talking about like being explicit and being flexible. You could have an application where the object could be larger than 4. If you actually did mean the last row, it might be better to do it that way.
Yep. So for posterity, the discussion is the 4 and the -1 here, even though in this case they give us exactly the same data, the same result, I and this person over there read them completely differently. So for me, the -1, it means the last row. I don't care if it has 2 rows of 5,000 rows, it's the last one. And that might be what you want, is your most recent data or your latest or your oldest data or something like this. Whereas the 4 means that's the 5th row. That might be what I want, but it means something totally different to me. The 5th row will always be the 5th row whether I have 5 or I have 5,000 again. So it's about the intent, but in this case, for this exercise, both of them are completely appropriate. So let me paste that up there. So we have multiple yellows. Have this one. You have this one. And you have this one. Okay. What about blue? (1D, 2D). 2D, so there will be a need for a comma. So along the first dimension, do I want contiguous elements, or am I going to skip stuff? If I'm going to skip stuff, I'll need 2 colons. Do I start from the beginning, or do I have an offset? I have an offset of 1. Do I go all the way to the end? Meaning, if I keep this pattern of skipping things, will my array end, and then that will be the end of my selection, or do I need to stop beforehand? I can just go until the end, right? And my step size is 2. And we can just run this for now. And that gives us, we don't have an entire selection yet, but at least allows us to debug the first dimension of our selection, of our slice. So 5 and 15, that looks pretty good. We have too many columns, but we're going to fix that in a second. All right, so what do we do for the columns? Do you want to skip something? Yes. So 2 colons. Do we want an offset, or do we want to start from the beginning? Start from the beginning. I'm going to put in the step size already. I know it's a 2. Where do I want to stop? Yeah. 3, 4, -1, -2, they would all work. Or at least in this case, again, they would give us all the same result. I don't really have an intent here. So we're going to do an exercise in the second where the minuses will matter. But in this case, they're all valid. So we have blue, blue. I'm going to put a positive and a negative up there. All right, any questions on this one? No? Anything surprising, confusing? Totally natural? It's good. Yes?
If you want to make a copy of a 2D array, is it like a good practice to use 2 lonely colons?
2 lonely columns. So the question is, if I want to make a copy of an array, do I need to use the 2 lonely colons? It's actually a really good question, and I think it's the next thing in the slides. So let's demonstrate this with a simple array. So I'm going to create an array here. 1, 2, 3, 4. Just a trigger warning. This is going to upset some people. So I have an array B here, which is a slice of A. Right, I'm going to take the first two elements of A. So A looks like this, B looks like this. So far, so good. I go in B, I take the first element of B, that's the 1, and I replace it by a -1. So this obviously modifies B in place, but not so obviously also modifies A. Right? This is happening over here. So what happens when I do this slice here is that B is a new array. It's a new array object, but it's not new data. So you have some buffer in memory of some numbers. We'll talk about that towards the end of the tutorial, if we have time. Hopefully we'll have time. And what happens is this buffer of data represents some numbers, our integers here. And when we express a slice, what happens is we create a new array that in this case points to the same location in memory, but only looks at the first two elements in the array. So you have two arrays that share the same memory. So when I go in here on sort of row 52 and I replace the 1 with the -1, I'm not modifying the array B itself. I'm modifying the an element in the buffer in the memory that is shared by multiple objects. So the result is that it appears as A and B have both been changed, which is both correct and incorrect. It's not that A and B have changed, it's that the memory has changed and that we can reach that memory using two different names. We can call it A and we can call it B. Some of you might think, oh my God, this is evil. It can lead to unpleasant surprises if you're not careful, but it has benefits as well. Doing memory allocations and memory copies is expensive in the grand scheme of how fast computers go. So sharing the memory is actually a pretty good idea. It's also very efficient. You can have multiple views into the same array, the same memory, without having to make copies of everything. And the question is, so back to the question, if I made A : like this, it would still be a view. So that's not the solution. Arrays do have a dot. If you do need to make a copy of the data, there's a .copy method like this that takes the data that is viewed by A and reallocate an entirely different memory buffer. So then they're completely separate from each other. So there is no, like in MATLAB, for example, there's something called copy on write, where if you're reading data, you're reading a view into the same memory data. But if you're about to write something, then MATLAB, the write will be slow because it'll actually copy the data and you'll write in there. Not in NumPy. It'll just write into the same memory, for better or worse. Mostly better, I think. All right, and one more thing about slicing, and then we'll take a short break, is that these slices, so we can use slices to sort of get data at a given sort of location in our array, but these slices can also be interpreted as sort of coordinates in our array that are spaced in a certain way, and we can assign to them. So they're usable not only for sort of getting data, as we're doing here, selecting the last two elements of A, but we can also insert values here, as long as it has the same length. So we're replacing the 3 and the 4 with the -1 and a -2. So that's completely reasonable thing to do. And you can also replace with a constant. we're going to see in a little moment after the break something called fancy indexing or masking or Boolean indexing that allows you to do this not necessarily based on the position, but based on the values itself. The values themselves, which is pretty neat. It's a nice way if you're trying to like threshold some data or something like that to select all data that is below a certain value. You just want to set it to 0 or something like this. So it's sort of the next step in that idea of slicing. Okay. Any questions before we break for 10 minutes? I'm maximizing for snacks here because the snacks are supposed to be here at 2:25 and I plan of having a break now at 2:25, haha. And then they're there until 4, so I plan on taking another break, at least one other break before 4 o'clock. So you can maximize jelly bean consumption. All right, so I'll see you at 2:35. Hope you found all the candy, all the coffee, all the snacks you could find. I see some gummy bears over there. No, I'm good. Thank you. I'll be back here again this week, so I'm sure I'll get my fill. Thank you. I had a good question during the break about when to use parentheses and when to use square brackets. So I thought I would talk a little bit about that. It's not just about NumPy, it's about Python. If you're just starting to use Python, you can sort of semi-ignore what I'm about to talk about. I'm going to talk about how Python works sort of underneath the covers. If you're sort of interested in that, hope that will be interesting. If not, this is the part of the class that you can just like, I don't know, look at Twitter for a second or something. So what do square brackets and parentheses do? So when I do a square brackets, let me make that a little bit bigger. A square brackets 0 here. The square brackets are what's called syntactic sugar. Has nothing to do with the sugar you're eating right now. For a call to a method named getItem with the argument 0. So writing this line of code here, $_getItem, parentheses 0, would be really annoying. So the Python language provides this syntax here, therefore that is sweeter, therefore the syntactic sugar, to signify that you want to get a value at certain coordinates. And also if I say at square bracket 0, I want to set 100. This gets translated to a call to a method named setItem, where the first argument is the coordinates, the 0, and then the second argument is the value that I want to put in there. So this assignment to square brackets gets translated to this method call here. So every time you use square brackets with dictionaries, with lists, with NumPy arrays, with pandas data frames, with, I don't know, this morning I was in a tutorial about working with satellite images with a package called SciPy. Sometimes we're using square brackets to get data for a certain image channel. The square brackets would call this setItem and getItem methods. And what do the parentheses do? So if I do np.array and I pass in some data here, the parentheses, what they do is that they call a function. Again, they are syntactic sugar for calling a method named $_call. And then you're probably asking me, wait, don't you need $_call on $_call because it's parentheses on the method? And that's the point where like Gil might be to explain the logic, but it's sort of, I stopped there. Below that point, I'm like, there's a $_call, I know what it means, and I kind of sort of understand what happens after that, but I stop here. So these methods with the double underscores, people often call them dunder, You might have heard this name or read this name in some blog post, maybe on the internet. They're called dunder methods, and they're all over Python. That's how Python works. There's a dunder len to get the length of an array, for example. Yeah, like this. There are things to do iterations, how Python works with for loops. They're called, dunder methods, or also called in the documentation special methods, and they are part of what's called the Python data model. And if you want to learn more about those, there's an amazing book called Fluent Python that I highly recommend. Not a beginner book, but by far the best sort of medium to advanced Python user. Should be on your list if you plan on using Python in your life. Let's do another exercise, a little bit bigger. Again on slicing. So the exercise that I would like to do here is called filter image. So if you want to open this in your editor of choice, I'm going to do it here in Canopy. If you're using Spider, you can open it in Spider. If you're using it in a notebook, you can take the code and paste it in a cell, or Jupyter Lab. And I'm going to walk you through a little bit of what this exercise is trying to do, because it's a little bit tricky. And in this exercise, at the bottom, there's some starting code, and it requires you to open an image. And the image is what's called a relative path. It's looking for an image that is in the same folder as this script. So depending on which editor you're using, you might or might not find the file. If you cannot find the file, please raise your hand, and Glenn and Gil will go around to help you find the file. So in Canopy here, I'm going to change the editor directory, and I'm going to run this. So it should show me this fiery photo of the DC Metro. And what we're trying to do here, or your task, will be to blur this image. So some of you might be image processing experts. This is a slicing exercise that disguises itself as an image processing exercise. So I know that there are better ways of doing this, but that is not the point. I know that we're going to be throwing away some data because our image is going to get smaller and smaller, but that is not the point. Here it's about the slicing. So what we want to do for blurring the image is that we're going to compute the blurring of the image as taking one pixel and then averaging it, which is with its immediate neighbors, and that will give us the blurred version of that pixel. And the idea is that if we do that everywhere, the image is going to get a little bit blurrier. Since I don't know how well it'll work if I go draw on the whiteboard, I started doing these amazing little drawing earlier, so I'm going to keep on doing this. So what I'm doing here is I'm breaking apart the problem, or I'm taking apart the problem of this image processing that I want to do, and I'm creating the smallest array possible that still exhibits the behavior that I'm into. And when I work with NumPy, I do that all the time, and I encourage you to do the same. Take your graph paper, take white paper, draw arrays. If you have a 5,000 by 5,000, don't draw a 5,000 by 5,000. Draw a 4 by 4 or 10 by 10, just as big as you need it to be so that you can make your data selection, your slices as you want to. So conceptually, what I want to do here is I want to take these blue X pixels, and I want to sum them up together, divide by 5. So I want to do their average, and the result will be this other X on the right hand side. That will be the blurred version of that pixel. Then I'm going to do the same thing with these beautiful pink circles. right? So this pink circle here is the average of these 5 other pink circles. I'm going to do light blue squares. And I'm going to do beautiful red hearts. Well, sort of hearts. You know what I mean, right? Beautiful. Oh my God. Just try it. Try drawing with the trackpad. Don't laugh. Okay. Oh, wow. So we look at this, and I see it in your eyes when I describe that I want to have this cross all over the image. I see it in your eyes that you think, I'm going to write 2 for loops, one with an I, one with a J, and I'm going to do like the center of the pixels of this one, plus 1, minus 1, etc. But no, this is a NumPy tutorial. You're not allowed to write for loops. Sorry, I didn't make that clear at the beginning, but you're not allowed, unless I give you the permission. So the question here is, how do we express this blurring algorithm without using for loops? So remember, the averaging, the summation that we want to do is the top pixel of the x plus the central pixel of the x plus the left plus the right plus the bottom. Yes? Okay. So what do these 4 pixels have in common? Anyone? I heard something earlier. So this one in the upper left here. Yes? Yeah, they're centered. We're throwing away the first column and the last column. That's right. But this blue X here is the top pixel of the blue X. Yes. Then I have a top blue square, a top pink, and a top heart. Right. So conceptually, these here in this beautiful green, they're all top pixels. Do you see that? Right. So this one here is a top blue. This one is the top light blue, top heart, top circle. Let's do another one on the left here. I'll print it out and send you postcards at the end. No. What do these here on the left have in common? They're all left pixels, yeah. This is the hardest thing in the world. They're all left pixels. And you can imagine that if I draw a square around the center pixels, it's because they mean they're all center pixels, etc., etc. So what's going to happen if I do this? Perfect. Make it black. That's not going to work. All right, so what I want to do here is that I want to take my image, have my entire image here, and I want to slice that represents the top pixels. What's a slice that represents my top pixels here? Zero colon 1. So if I do 0:1, the upper bound is not included, so that's not going to work. I think you meant 2. It's okay. Off by 1 errors are completely acceptable. Okay, so those are for the rows. And on the first 2 rows, what are my column selections? Louder? Yes, 1, colon 3. Right, so that's column 0, column 1, and all the way to column 3. And what are my left pixel selections? What is the row? Where do I start? Yeah, 1, colon 3. And for the columns, funnily enough, it's exactly sort of the mirror thing of the top pixel selection. All right, so what am I going for here? What I'm going for is imagine I have this image as like a translucent printed on a translucent plastic thing that like our old school professors use to do lectures, or just a slide. And what I'm going to do is I'm going to make 5 copies of this, and I'm going to cut out rectangles. Like I'm going to cut out edges in the bottom. Those will be top pixels. I'm going to do the same thing with the left and the right, same thing with the center, same thing with the bottom. And then if I take these 5 images, they're a little bit smaller, but all the same way, and I stack them on top, sorry, microphone, and I stack them on top of each other, and I shine a really bright light through them, because now I'm adding a lot of density. What I'm going to end up with is a blurred image. Right, so I'm doing a similar thing here, but in NumPy. These slices here are a little bit like me cutting out the edges of my images. And then if I add them all together, you'll have to fill in the blanks and do left, right, and bottom, etc. If I add them all together and I divide by eventually 5, I'll have blurred my image. So your task here is to figure out the correct slices for the top, left, right, center, and bottom slices of my image. And I recommend using relative slices, because this one here, these coordinates will work only on my little 4x4 image. They won't work in any arbitrary sized image. But there's a way here to specify those slices that will work in a 10x10 or the 500x500. And I'll just add 2 lines here at the bottom so that you can show the blurred image as well. Show blurred CMap. So what's happening here is this will create a figure and draw the original image. This will create a new figure, blank. And on the new blank figure, it'll draw the blurred version of your image with this, what's called a color map. So it's a mapping of each numerical value to a color. And the one that we're using here is called hot. And that's the one that goes from, I don't know, dark red to yellow. So we'll work on this for 15 minutes probably. We'll be walking around if you have any questions. So that we can do more of these, I'd like to stop now and look at the solution. I understand that this is kind of a tricky exercise to wrap your head around, because you're doing slices, you add them together, and then magic happens, like for loops and things, and then you get a blurred image, and it might not be obvious why this is happening. So I'm going to open here the solution file because it has a solution. And also it has another solution, which is the one that I know you're all dying to write, which is the one with 2 for loops. And I would like to do also a performance comparison between the two to sort of convince you that you should actually really learn NumPy. So my first solution uses the slices, the ones that I'm trying to push you towards using. And if you sort of ignore the spacing here, in this sort of weird place to put spaces, there's a sort of a pattern. I'm not following the usual sort of Python formatting standard here. I thought it was much easier to just align all the colons together because it's easier to read. But there's a common pattern with the 1 - 1 or the -2 or the 2 colon, which basically means I read this as throw away the first one, throw away the last one, throw away the first one, throw away the last one. So those are center pixels. I'm throwing away the edges. Top pixels, I'm throwing away the bottom 2 pixels and the sides. Bottom pixels, I'm throwing away the top 2 pixels and the sides, etc. And if I run this, it should create 2 images. I don't know if we'll, oh yeah, it renders kind of okay on screen. The original and the smoothed one, they're very, very, very similar. It's very hard to realize whether you've blurred anything or not. But if you do the difference as suggested in the exercise, you'll see this sort of shimmer, and that's the sign that you've actually done something. That's the result of the blurring. And if you've tried doing the bonus where you apply it 50 times, you end up with an image that's 100 pixels smaller in each dimension, but you get something that is definitely blurred. Unless you're nearsighted, in which case if you take off your glasses, all of them are blurred, but that's different. So what I would like to do here is to compare this NumPy solution and another solution, which is 2 for loops. So I'm creating at first an array of zeros, and then I'm looping through the number of rows and the number of columns, and I'm doing the same thing, taking the center plus 1 pixel above, 1 pixel below, 1 to the left, 1 to the right, and their center pixel. And I'm going to use this IPython magic called timeIt. And what timeIt does is that it's going to run my code a bunch of times and tell me roughly how long it takes to apply the blurring or the smoothing. So about 700 microseconds per blurring call. So if I try the loop one, how much do you think is going to be slower or faster? Slower. How much? Twice? 10? 1,000? Price is Right rules. Right? As close as possible, but no higher, otherwise you're disqualified. Who says 2? Who says 10? Who says 100? Who says 1,000? Okay. Who says more than 1,000? It would be kind of extreme, more than 1,000 times, but okay, let's see. Ooh. Right, it's 1,000 times faster, more than 1,000 times actually. So we have 1 or 2 winners on that side of the room. You can get more candy later. So that's a huge benefit, right? There are not that many things in code that will give you 1,000x speed up with, well, I understand it's a little bit harder to think of if you're really used to writing for loops. But hopefully after a little bit of practice, these NumPy slices will feel very comfortable activities. And it can have a huge, huge performance on your code. Yeah? Yeah, the question is, why is the NumPy implementation faster? What is it doing or not doing? So a big reason why it's faster is has to do with the data and how it's stored. So in Python, a list, or even in this case, what I'm doing is I'm getting out of here a Python integer, which is a whole object that has like a reference count, the value, a bunch of other things. And those have to be taken out and then put together and sent all the way to the CPU, and that's a lot of steps. Whereas in the NumPy array, the memory buffer, the memory location, the bytes that are there are the number, and they get sent to the CPU as is, basically. So there's no like pointer resolution and that kind of stuff. The other thing is there are for loops happening here. but they're part of how NumPy is written, which most of it is written in C. So there are C for loops happening there that have very low overhead versus the 2 levels of Python for loop overhead that in what's called a hot loop like this cost is a huge overhead, and that's a lot of where the cost is. Yeah. So there are cases where writing for loops is the way to go, but for numerical stuff, as much as you can avoid it, the better it will be. Other questions? Okay. Our next topic is an extension of the indexing that we were doing. And it is a somewhat official name called fancy indexing, also called masking or Boolean indexing or logical indexing. The story that I've heard is that many, many years ago when NumPy was young, there was an exchange on some newsletter, and I think it was Eric Jones, who's the CEO of Enthought, who called this fancy indexing, this fancy way of doing indexing, and sort of the name stuck for years and years. There are still spots in the NumPy documentation that will use this name. So what fancy indexing allows you to do is to index not just by position like we've been doing, but also by value, basically. So it takes 2 forms. One on the left-hand side here that we called indexing by position. And we're indexing into this array here. So it goes from 0 to 80, upper bounds not included, in steps of 10. And this form of fancy indexing, in the square brackets where we're getting an item, what we're passing here is an array or a list of integers. And what happens is that NumPy is going to return all the values that are at these given positions or these indices. So we get the element at position 1, the element at position 2, and the element at position -3. So, and these coordinates, this list of indices, like we've seen over and over again, we can get items at that position, and we can also set items at that position. So here, notice how the 10, the 20, and the 50 have been replaced with 99s. This is useful if, for some reason in your algorithm, you know where your data is. You can use that to either select or replace data or do an analysis on a subset of the data. The other form of fancy indexing, called Boolean indexing or masking, the idea is to put in the square brackets here a Boolean array, an array of true and false, that will basically be used to select the data. So if it's true, I think of it as like overlaying a piece of paper over my array. If it's true, I'm going to cut out a hole, and everywhere there's a hole, that data is going to come through. And if it's white, then I don't see the data anymore. So I'm using that here, and we're doing this kind of strange thing, I must admit, which is to build a mask by hand with 1s and 0s, and setting the type of this array to be Boolean. And the idea is the 0s will become false, the 1s will become true. The odds of you doing that for real is about 0. So I will show you a more realistic way of creating a mask than doing it by hand like this. So let's say I have, again, the famous array A that has some negative numbers in there, a positive and some positive numbers. And I want to threshold my data. There are a few different ways of doing this, but I find the masking approach to be very clear. So what I want to do is I want to identify where is the data that's negative. So I'm going to make a comparison to a value here. And this is a vectorized operation. NumPy will do element-wise comparison of A with the constant 0. If it is less than 0, my mask or my Boolean array is going to be true. Otherwise, it's going to be false. I can call this mask, for example, or actually, let's call it negative, which is a much better number, better name, sorry. And then I can use that in my square brackets to get the item that are negative. And so this is getting items based on the value of the mask, and I can also set items. So I'm going to threshold everything that's negative, right? Everything where I have cutouts, holes that are true, I'm going to go in and paint a 0 in there. All right, so all the negative numbers in my array have been replaced with a 0. Any questions? Okay. So let's see that applied in 2D. These two methods. So first in yellow, the selection of elements on a diagonal. There's a method in NumPy that can do that for us called diagonal. But let's say you don't know about it, but you know about indexing. We're selecting these yellow elements here by passing two lists of integers, and you can think of them as list of coordinates. So 0, 1 is row 0, column 1 is the 1 here. 1, 2 is 12, 2, 3 is 23, 3, 4 is 34, 4, 5 is 45. Oh, look at that. Yes, 4, 5 is 45. So that's row 4, column 5. And they don't have to be on a diagonal, they can be anywhere in the array. Then in light blue, we're mixing regular slicing with fancy indexing. So we're going from row 3 until the end. So we're concerned here with the lower portion of the array. And if we just look at the selection in the array, we see here that there's a step size of 2 and then a step size of 3. Definitely not something we can do with slices, because that would mean that we need two different third argument to the slice. So in this case, we get fancy indexing to the rescue. We pass a list of indices. We want column 0, column 2, and column 5. And then finally, in red, we're mixing masking, right, the second form of fancy indexing, with regular indexing. So we're creating a mask here where we want the first, the third, and the last element. And we're applying that on the rows. So that gives us the first row, the third row, the last row. But we're only interested in column number 2. So that gives us the 2, the 22, and the 52. Okay, so your turn now to try this. So same starting code, create a square array 5 by 5. Then I want you to extract the elements in light blue. The ones in your slides, if you have them open right now, it's the same diagonal as the demo, and you know the answer already, so I changed it to be much harder. Not really. And yeah, so please select these elements in blue and then create a mask that allows you to select all elements that are divisible by 3. Let's have a look at the solution so we can have another short break and have more candy. So first step, I wanted to select these blue squares, these blue cubes. I did not specify an order. So let's say I said from the top left to the bottom right, right? That's what you did? No, maybe? Let's say that's what I said. So square brackets, right? Because we want to get elements at given positions. And because we know the coordinates, or we're going to come up with the coordinates of each point, I'm going to use the form of fancy indexing where I'm passing lists of integers. So what are the coordinates of the number 2? 0, 2, I think. Let's see that. Yep, so far so good. That's our first one. What are the coordinates of 13? 2, oops, not like this. 2, 3. That looks good. What are the coordinates of 16? 3, 1, and then same row, so that's a 3. Aha, minus 1. But also 4, yes. Everyone get that? This is a little bit, to be honest, this is a little bit like the building a Boolean mask by hand. Very often you'll get this data here, these two lists, as the result of other computations, but I still think it's very important to understand what's happening. What's the behavior if you're passing a list of integers? How is this interpreted by NumPy? All right, what about the second one? Did anyone figure out how to select the numbers divisible by 3? Yeah.
I created a mask where it said a modulo 3 equals 0.
Yes.
Apply that to the a array with square bracket.
Okay. So the first step, I assumed possibly wrongly that you knew this operator called modulo. And what modulo is the remainder after integer division. So just a few examples here to sort of explain the behavior of modulo. So if you divide 4 by 3, there's 1 left. If you divide 1 by 3, there's also 1 left. And 3 by 3, there's nothing left. So if we take advantage of that on our array and we divide by 3, all the places where there's 0 here are numbers that are divisible by 3, assuming that 0 is divisible by 3. But let's just say it is for now. If I take this and I put it directly in my array, something very strange is going to happen, which is not what we're looking for. Right? What's being interpreted here is that we're passing a list of integers, and this array here is row 0, row 1, row 2, row 0, row 1. That's row 2, row 0, row 1, row 2, row 0. So you're now went from 2D to 3D, not what we wanted. And I know there are moments where you want this, but this is another one that breaks my brain, that I usually find a different way of doing this than that. So that's not what we want. What the behavior that we're getting here is the first version of fancy indexing. We're getting a list of positions. So instead, what we're after is a mask. So if we test equality to 0 here, that's what we're interested in here. That array has exactly the same shape as A. So that if we use this a modulo 3 equals 0 mask in there, that gives us only the numbers that are divisible by 0. Divisible by 3. Hope you finished all the jelly beans. Until tomorrow. I'd like to take a few minutes to talk about how to reason about higher dimensional arrays. So what we have here is an illustration of a 1D array, a 2D array, a 3D array, and I must admit my limits as a human, my visualization of a 4-dimensional array, which is 2 3-dimensional arrays side by side. I assume you have similar limitations to mine. So the other things that we see in this slide is just above each of the arrays is a tuple that represents the shape. So our first array here is a 4 comma. So it has 4 elements. And above, the arrow points towards the direction of of that particular shape, and the 0 relates to the element inside of the shape. So here it means that 4 is pointing towards the your right, means it's a 4-column array basically. I'll get to the reference system at the bottom in a second. Then our second array is a 2x4, 2 rows, 4 columns. So now the 0, which is the 2, points down, is the number of rows, and then the 1 points across columns. Then when we do a 3x2x4, now the 0 is the depth of our cube, the 1 is the height, and the 2 is the number of columns. And now when we go to 4 dimensions, the first element, the 0, sort of is the meta dimension, is the one across cubes. Excuse me. The 1 is the depth, goes inside of the screen, the 2 goes down, and the 3 goes across columns. So what's happening here, one way to think of this is, let's say we are a car manufacturer that makes electric cars that starts with a T, and we're measuring, like, I don't know, brake performance or something like this. So we have sensors on the front right brake, and we're keeping samples as it goes, and we have 4 samples worth of data. Then we are like, it'd be good if we had front right and front left. So we have 2 sensors per car, and for each of those we have 4 samples. Then we have now 3 cars, 2 sensors per car, and then 4 samples per sensor. And then we have 2 cars in Vermont and 2 cars in California. We have cars in Vermont, cars in California, 3 cars in each, 2 sensors per car, and then a certain number of samples. So as we're adding new dimensions, we prepend them. We take existing dimensions and we push them down, and new dimensions are put to the front. This is a consequence of NumPy being what's called row major, like the C family of languages, and is completely the opposite of MATLAB and Fortran, which are column major. So in Fortran and MATLAB, what you do is you append dimension. In MATLAB, the 4 would be a column. The 2, you would add 2 columns, and then you would add like a depth in the cube. So you would append dimensions. The consequence of the row major structure is like the 0, the first number that you see keeps on changing, right? The 0 starts pointing that way, and then it goes down, and then it goes in, and then it goes across cubes. Another way to think of this is to use negative indices, right, relative to the end of the shape. And that has a really nice property, which is -1, the last element of the shape, is always pointing the same place. The 4 here is always at the end, is always the last one, is always the number of columns. It's also, we'll talk about that later, all of the elements that are contiguous in memory, typically. Not all the time, but very, very often in NumPy. So it means these 4 numbers are next to each other in that memory buffer that I keep on talking about, which means that any operation that reduces those numbers will be a little bit faster than going sort of across, sort of jumping through this memory buffer. Any questions on these higher dimensional arrays? Mm-hmm.
The top dimension then is the axis that is always in arguments.
The question is about these tuples?
When you reshape something and part of the argument is axis equals
Yes.
0, 1, 2, 3.
Yeah. So the question is, how does this relate to this axis keyword that if you've used NumPy is everywhere when you do reduction operations? It is definitely related. That 0 here, or that -1, would be an axis value.
Those would be valid values.
Yeah. So axis 0 would be the 2, axis 1 would be the 4, and axis -1 here would be the 4, and axis -2 would be the 2. Yeah, so you can also use negative indices when using axis, which is super nice because -1 is always the last one. But I'm getting ahead of myself. I think now my slides are triggering questions that are 5 slides into the future, which is just a bit too far. Actually, let's jump right there. There are a few things here about creating arrays. We'll come back later. I think I'd rather have enough time to give you enough time to do this computation section. The rest, I think you'll know enough by the end that you can figure it out. So let's jump over a few things to cover this section that we call calculation methods or calculations with arrays, which we'll address in just 1 second, this axis keyword. So I think we have similar page numbers. I have 38 here. The slide is called Computation with Arrays, and we've sort of summarized the main rules when doing computations either between or within NumPy arrays. The first one says operations between multiple arrays are first checked for shapes. These rules are officially called broadcasting rules. There are a few slides later that I might get to. Actually, that I'll get to in a second. Let me go through these rules first, and then I'll talk about them separately. So, proper shape match. Some of you have experienced the consequences of this in the image blurring exercise where you might be getting, I forgot the name of the error, but a shape mismatch error saying your two slices were not exactly the same shape, and then NumPy would complain. So that's one example of these rules. The shapes have to be exactly the same, or they have to be compatible, and we'll see what it means to be compatible. Rule number 2, every operation is done element-wise, even multiplication, even division, even exponentiation. Rule number 3, reduction operations, which is the main topic of this section. So if you want the mean of an array, the sum of an array, all the statistical moments, by default, it'll take your entire array and collapse it into a single value. Unless you specify this thing called an axis, which allow you to specify which dimension you want to do your computation over, which we'll see in a second. And then finally, in NumPy, there is this concept of missing value that's represented with something called a nan, N-A-N. So nan is a special floating point number, and it has this particularity that if you add not a number, that's what nan stands for, to another number, you get not a number. So if you have an array that has not a number in there and you try to add things together, you'll get not a number at the end. I think of it as like poison in the well, right? If there's one nan, it'll just propagate and then there'll just be poison everywhere. Floating point poison. All right, so let's see a few examples of rule number 1. And if we jump straight to, I think it'll be page 47. I have an illustration of these rules, these broadcasting rules. So the simplest way to think about broadcasting is this case where my 2 arrays over which I'm doing operations have exactly the same shape. I have a 4x3, I have a 4x3, I add them together, and I get element-wise addition. The second case of broadcasting, which is pretty common and not too tricky to reason about, is you have a 2-dimensional array and a 1-dimensional array. So I have a 4x3 and a 3 comma. And if I add them together, what happens is the one that's shorter gets broadcasted, gets added in this case to every single row in the larger array, right? Without requiring any memory copy, which is pretty great. It's really efficient. There's a for loop happening somewhere. Again, we're not the ones who wrote it. It's part of the NumPy implementation. but we end up with the same result in this case. And finally, this one is funky but super powerful, is we have a 4 by 1 and a 3 comma, and those can also be broadcasted together. The column will be sort of repeated horizontally, the row will be repeated vertically, I guess. Well, will be repeated one way and repeated down, and you'll still get a two-dimensional array as a result. The way to think about this they're presented in on the previous page, page 46, where there are two rules. Rule number one is given two arrays that have different shapes, is it possible for NumPy to prepend ones to the smaller array's shape? So if I have, for example, in this case, an array of ones that is 3 by 5, and an array of ones that is a 5 comma, I can, prepend a 1 to the 5 comma. So now both of them are 2D. So if I can do that, it's fine. And if the two arrays have the same number of dimensions and some of them are 1, some of those dimensions are 1, they can be repeated without copying. There's too much stuff happening in this slide right now, so let me go to Canopy instead, or to IPython. How am I going to do this? So let's say I have an array. I have two arrays. I'm not even going to run this code. I just sort of conceptually want to talk about it. So A is a 5 by 3, and B is a 3 comma. So if I try to add them together, right? If I try to do A plus B, what's going to happen is NumPy is going to right align the shapes like this. In the case of B, it is possible. Rule number one, can NumPy prepend a 1 like this? Yes, that's possible. It doesn't change the total number of elements. And rule number 2 says if it's a 1, then that array can be repeated. So it means that this array here can be repeated 5 times, and you'll have 2 elements that have exactly the same shape. If I have another example where A is a 5 by 1, and the other one is a 3 comma, right? If I look at this, I'm like, A and B have completely different shapes. That's never going to work. But rule number 1 says align the shapes together and prepend ones if you can. Now both of them have 2 dimensions, and this is going to be repeated 3 times, and this one is going to be repeated 5 times. That's what's happening down here. Whoops. Right, down here I have a 4 comma 1, and here I have a 3 comma. Just like, and they get, one of them gets repeated horizontally or across columns, and the other one gets repeated across rows. All right, so let's go back to this, to our rules. Rule number 2 said Elementwise Operations. We've seen that quite a few times already. So let's go to rule number 3, which is the following page 39 probably. So our starting point is a 2-dimensional array, 2 rows, 3 columns. And the code on the left and the blocks on the right, they go together. They go hand in hand. So our first example computes the sum of our array A. And it does that using a method. So a method is like a function attached to an object. So here the sum method is attached to the array A. And I'm not passing any arguments. So what happens is that all of the values in my array, they gets collapsed together into a single value. So the sum of all these numbers is 21. If we don't want the sum over the entire array, but we only want to do like column-wise or row-wise, we can specify this keyword called axis. The axis is the element of the shape that will go away, is the elements of the shape that will be sum or be you'll get the mean of it or the product of it or the variance, etc. So here we're doing the sum of this two-dimensional array along axis 0. So we get the 1 plus the 4, the 2 plus the 5, the 3 plus the 6. And that creates a new array that has 3 values, right? Because we got rid of the first dimension, that was a 2, and we're left with only the 3. And that axis can be positive, it's very common, but it can also be negative. Here we're doing the sum along the last axis, and the last axis is always columns, so we're collapsing our arrays like this. So that gives us a two-dimensional array, a 6 with the values 6 and 15. So
Does pandas follow that same logic?
if does pandas follow that same logic? Totally. Was that your question?
Yeah.
Yes, it does, and it even allows you to say axis equals rows and axis equals columns. So let's say, sorry, this has to be a tuple. I have an array A here. That's an array of 1s, 5 rows, 6 columns. And let's say I don't remember what this axis keyword does. So I'll do, for the first, I don't know. I've been using, let's say, MATLAB and NumPy for 15 years. Oh my God, yes. For the first 13 of those 15 years, I never remembered what axis did. So what I would do, which is a trick that works 100% of the time, is I would try one. Right, I would take my array and I would look at the shape. I would keep my fingers crossed that it's not square, because otherwise it's really hard to know if you're doing the right thing or not. I would just look at the shape before, and then I will do my computation. I think I want to do along axis 0, and then I would look at the resulting shape, and then I would think for a second, am I expecting 6 values, 1 for each column, or am I expecting 5 values, 1 for each row? And let's say I did not register my experiment before doing this. So let's say I wanted 1 value per column. I look at this, that's a 6. Yep, that's what I want to do. I'm going to remove the shape. That's my computation. Another way to think about this, so what happened in the last 3 years or something that I realized is the axis that you specify is the element of the shape that will go away. Right, so I have a 5 by 6. If I want, and I know that I have 5 rows, 6 columns. I know I want 1 value per column. I'm going to get rid of the 5, which is axis 0. So the value that you specify, the shape that the axis that you specify is the one that goes away. So if I was using the 4D example of earlier, and I'm working in 4 dimensions like this, and I want the, I don't care about the car difference, but I want to do a cross car. I do care about front right from front left. I would get rid of this 3 here. Right, so I had Vermont and California, 3 different cars. Each car has 2 sensors. So I want to get rid of the 3. That's axis 1. If you don't remember this rule, I would try them all until I'm like, yeah, I think that's the shape that I want. So obviously sum is not the only function method that exists on NumPy arrays. On the right hand side here, there's a handful of the sort of common mathematical functions, like the sum of all the elements, the products of all the elements, the min, the max. We'll talk about this argmin and argmax in a second. Those give you the position or the index of the minimum or the maximum. There's PTP, shorts for peak to peak, which is the difference between the maximum and the minimum either in the entire array or per column or per row. You have all the statistical moments, kurtosis, skewness, etc. And you have some to get the truth value of an array. What that means by this is an array considered true if every single one of its elements is true, or if only some of its elements are true? And on the left-hand side here, what we see is that these methods that I keep on talking about, they also exist as functions. In the beginning of NumPy, there were only functions, and methods were introduced later. At least that's the story that I know. Both of them work fine. They work the same way. There's not one that is really much faster than the other. One benefit of the function form is that if A is a list of list of list, for example, by passing it here, it will be converted to a NumPy array, and then you'll use the NumPy sum, for example. So you might get a speed up at the cost of some memory. But it does accept this access keyword just like the methods. So let's do a short stop with min-max. If you're coming from MATLAB, min and max, you return a different number of arguments. Depending on how many arguments you specify, it'll give you the min and the max, or the min and its position and the max and its position. But in Python, it's two separate functions. You have to do it in two shots. Here we have a two-dimensional array, and computing the min of the array either as a function or as a method, just like max will give us the minimum, just like sum will give us the minimum for the entire array. If you do use an axis, just like sum, it will collapse over a given dimension. So this will give us the max of each column. In this case, it will give us the max of each row. And if you want to know where this max or this min is, you can use argmax and argmin. So the argmax of our two-dimensional array is at position 1. And the tricky part here is that it takes our multi-dimensional array and flattens it into just one long stream of data, which is kind of annoying, right? Because usually we care about the fact that our data is multi-dimensional. There's this super helpful function called unravel index, where you pass in your linear index through your array and the shape of the array that you want to sort of resolve that index in. This is something you could do with the modulo and a floor division. You are 100% guaranteed to get it wrong the first time. So just use unravel index. It has a name and it will work every time. So an elegant way of finding the position of the max and then finding the coordinates of that maximum. It does have one downside, which is if there are multiple maxima or multiple minima, it'll only give you the coordinates of the first one that it encounters. That's where this function here called where is useful. There's a lot of stuff on these slides. Let me do it in Canopy instead. Do np.array -1 1 5 0. So I can use np.where to find the coordinates of the elements that are non-zero. So what do I mean by this? Is let's say I want to find Actually, let me do that again. I'm going to do 2 5s. I want all the coordinates of all the values that are equal to the max of A. So there are 2 trues in here, and I want to find the coordinates of these 2 numbers. So I'm going to pass this mask to where here. And where, kind of like shape, it's always going to return a tuple. And that tuple is going to internally have as many arrays as there are elements in the shape. So here I have 1 NumPy array, and it says along the first dimension, if you go to position 2 and position 3, you'll find these 2 trues here where they're coordinates of the 2 maxima. And I don't have to test for equality. I could test for where are all the numbers that are greater than 0. That also work as well here. Okay. Any questions before we jump into the next exercise? No? Okay. So our next exercise is another one like filter image, a larger exercise called wind statistics. And it also relies on data, just like our filter image relied on the DC Metro. So either copy the data next to your notebook or update the path to the data inside of your notebook. If you have issues and you cannot find the data, please raise your hand immediately. This is not an exercise about finding data. It's an exercise about NumPy. So we will run to your rescue so you can actually do the interesting part of the exercise. So let me say a few words about it first, and then I'll give you some time to work on it. So the data that we're working with is wind speeds recorded at 12 different locations in Ireland between 1961 to 1980, I think. So we have 20 years worth of data. The first 3 columns are year, month, and day of the data recording. And then we have 12 columns of wind speeds in knots. So the first step in the exercise says to use this function called load_txt to load the data. We haven't talked about it, so I'll just tell you how to use it. The file is called wind.data, and the file is clean. You don't need to specify anything else. And this will load a NumPy array that has a certain shape, has 6,574 rows, 15 columns. So that's what we're going to be working with. So we're going to work on this for 20, 25 minutes possibly. There are 7 questions. I think you can make it all the way to number 7. The bonus is kind of tricky, and the bonus is very tricky. So if you make it to the bonus, there's enough stuff in the slides that I think we won't have time to cover. This thing called search, sorted, and reduce at. So if you make it to the bonus, you can look at the slides and maybe you'll be able to solve it. I personally had to look up the solution the first time. I had no idea how to do this. So, all right, let's look at the solution. So our starting code is still the same as what I typed before. So I'm going to run this again. And if I type data, right now NumPy is being kind, is only showing to me a summary of the data. Short aside here. So the way these arrays look on screen are set by something called print options. So there's a few options on like the precision of numbers, but also there's an argument called threshold, which is if an array has more than, I think the default is 1,000 elements, it'll show us the summary. So what I want to show you here is I'm going to set the threshold really big so that if I type data, it's going to show me there's like 100,000 elements or so. And now it's a mess. I often jokingly say that like for some people, which is completely fine, big data is data that doesn't fit on screen. Which is funny for people who work with like terabytes of data. It seems very quaint, but I think it's as difficult to go, not as difficult, but it's very difficult to go from data you can see to data you cannot see anymore. Right? It's sort of, it fits on screen, it fits in my head. It doesn't fit on screen, it doesn't fit in my head. It doesn't fit on screen, it doesn't fit in my head, it doesn't fit on my computer. It doesn't fit on screen, it doesn't fit in my head, it doesn't fit on a whole lot of computers. It brings its own set of challenges. So if I have this large array here that I cannot visualize, it's too much noise, I need other strategies to work with my data. And the two best tools that I know for big screen data is one is looking at the shape, and the other one is making plots. Because usually with plots you can easily see thousands and thousands of points and it's fine. So I look at this shape here, and I lied, I have another tool. Plotting, shape, and making slices. So if I look at my first maybe 4 rows, all right, that gives me, I get to see a little bit of my data, not all 6,500 rows. And I look at this and I'm like, oh yeah, so the first 3 columns, those are my timestamps, those are dates. And everything else, those are wind speeds. So right now in a single array, I sort of have 2 different kinds of data. I have timestamps and I have wind speeds. And if I keep them together, it's going to be really annoying because I'm going to have to separate them as we go all the time. So right up front, I'm going to take my data, I'm going to split it in 2. I'm going to do dates. So dates is every single row of my data, but only the first 3 columns. And then I'm going to call the other one I'm going to call the wins, which are every single row of my data, but from column 3, so that's the 4th column, all the way to the end. So now I have 2 different names. And because NumPy doesn't make memory copies here, because I'm just making a slice, this also be efficient. So I get clarity, and I still keep speed and memory efficiency. So it's win, 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 or something like that. Or I should say wind. Oh my god, this is bad. No. So I'll go to our questions. So question 2, we want the min, max, mean, and standard deviation over all the locations and all the time. So we want to collapse everything into a single value. So that would be wins dot min and wins dot max and wins dot mean and wins dot std. And if I run this, should print 4 separate numbers. Then we want to calculate the min, max, mean, and standard deviation at each location over all days. So there's in parentheses here, there's an extra statement. So we wanted different numbers for each location. So let's say I don't remember, let's say I'm going to do the min, which axis I want to do it over. So I'm going to look at the shape, and I see, whoops, sorry, I don't want to do it on data. I want to do it on wins. Am I expecting 12 values, or am I expecting 6,500 values? I expect 12 values, right? 1 for each location. I expect to take my long table and collapse it this way. That's axis equals 0. If you don't mind, I will turn off my print all the things, because otherwise this is going to be really noisy. So I'm going to put the threshold back to 1,000. There we go. So I'll just do the min here. It'll be the same thing for max, mean, and standard deviation. Then next one, I want a different set of numbers, one for each day. We're working with a 2D array here, so I assume that is the other one. If I'm not sure, assuming is bad, I'll look at the shape. I get 6,500 values. I think that's right. Right, one value per day. Then it gets a little bit more interesting. Now we're starting to see, we want to find the location that has the greatest wind speed on each day. So what's the method for me to do this? Argmax. And do I need to specify an axis? Yes. Which one? Let's say I don't know. So let's look at the shape. Get 65, so one integer for each day. That looks good, 6,500. And I can have a quick look at these values, and they look like numbers between 0 and 11 or something, which makes sense, right? There'll be a column number basically for each day. All right, then question number 6. I want to find the year, month, and day. So basically the timestamp on the day with the greatest wind speed. And there are quite a few ways to skin this virtual cat. What did you use? Which function or functions? Where? Okay. np.where of what? I want the where of the places where my winds are equal to the max value of my winds array. Right? So what's inside of the parentheses here is going to be a Boolean array, which is going to be true when max is equal to max. So it's going to happen at some point. And then where is going to return a tuple of arrays, which are basically coordinates. So row 2161 and column 11, that's where the highest wind speed ever recorded was found. So I'm going to take this here. I'm going to call that row and column. Any other way of finding this? Yep. I can take my winds, do the argmax of it, and it tells me that's element 25,943. And if I unravel the index of that in the array wind, gives me the same numbers. Right? I take my, gives me the same numbers. So that's row call. Anyone come up with a third solution? Third solution is to take my wind data and to calculate the max along axis 1. So it'll take my long table, collapse it this way. So for every day I'll get the max across all locations, and then I'll get the argmax of that, which will give me which of all the rows has the max value. So that gives me row, right? So 3 different ways. And then I'm actually interested only in the date. So I'll do dates, row, and that's December 2nd, 1966. And finally, I want speeds only for January. So I have this dates array here. First column is all years, second column is all months, third column is all days. and it looks like it's using one-based indexing for the months. So I can take advantage of that to say if my dates, all the rows of column 1, if those are equal to 1, right, it'll be true for the first 31 values, then it'll be false for a while. There'll be a bunch of trues again, false for a while, trues again, etc. Those are Januaries, right? Plural, as we know. So Januaries, if I look at its shape, it has 6,500 elements, right? The same number of rows as same number of elements as wins has rows. So we can take our wins and use Januaries to select a subset of the rows. And what that returns is still a NumPy array. It's just a little bit smaller, right? We took our big array and we only took some of the chunks. Every 12 months, we took 31 days worth of data. And what we want here is the mean, 1 per location. So we want to get rid of the days. We want to average over Januaries. Januaries, like this. Any questions? How did that one go? Harder? Okay. So there's one more topic I'd like to cover, and then I'll let you go, I promise. So we can all get, I guess outside will be cooler than inside right now. So we'll go hang out in the sun. No, probably not. So the next thing I'd like to talk about is how NumPy arrays are represented in memory. It is both an advanced topic and I think a very useful thing to think about. So if you know this, it makes a lot of NumPy data manipulation really simple to think about. So how am I going to do this? I'm going to try to draw things on the board. He's going to try to film me. And I'm going to run between the board and the microphone so you can hear me. Okay? I'm going to redraw exactly, well, almost exactly what's on screen. So above the blue line is what I've called memory world. And below the line is Python world. So in computer memory, there isn't really a multi-dimensional memory for now, kind of. It's just one long strip of memory where like there are addresses. Like it starts here. If you look here, from this point forward, you'll see data that corresponds to a NumPy array. But in the Python world, below the line, we have multi-dimensional arrays. So somehow we need some information to map between the data that's in memory to the Python that's in our, to the array that's in our program that we can use as a multi-dimensional array. And in order to do that, NumPy keeps track of a little bit of metadata. First metadata that it keeps track of is called the D type. We've talked about it before. So let's say that in this case, the D type is int64. Means every single element is a 64-bit integer. So it means that every single element takes 8 bytes, right? So 1 byte is 8 bits. If you do 64 divided by 8, you get 8. It keeps track of the shape and the number of dimensions. then it keeps track of where the data is. So it's basically, it's a pointer, it's like an address of where the data starts. And the last part, the really interesting part, is something called the strides. I'm going to write it down and I'll come back. So the strides, I think I'll use the next slide here. The slides is the number of bytes that NumPy has to jump over to go from one element to the other along each dimension. I will say that again while pointing at things. So to go from 0 to 3 in the original memory buffer, it has to jump over one element, 2 elements, 3 elements. So that's 24 bytes. To jump from 0 to 1, it jumps one element, so that's 8 bytes. Right. So the strides are what link basically the memory representation to the Python shape, or to the view in Python, in NumPy. So to go from 0 to 3, to go from this row to this row, 0 to 3 jumps 24 bytes. To go to from 3 to 6, 24 bytes. From 2 to 5, 24 bytes. 5 to 8, 24 bytes all the time. So go from 0 to 1 is just one element. 1 to 2, just one element. 3 to 4, one element. 4 to 5, etc. Now, what happens if we make a transpose? So there's an attribute on NumPy array .T that will do the transpose of your array. And what will happen if we look at the metadata is that the number of dimension will stay the same, still 2D. The shape will be flipped, but the strides will also be flipped. And the data pointer will be the same. The data stays at the same place. Like this. So doing a transpose like this does not trigger any memory copy. Right? NumPy doesn't need to copy the data. It has to swap the shape, swap the strides, and that's it. To go from 10 to 11, 2 different rows, now it jumps only one element, 8 bytes. But to go from 10 to 13, it jumps 3 elements, that's 24 bytes. Let's do 2 more. One of them will be a slice, and the last one will be fancy indexing. So my slice will be the first and the last columns. So the resulting shape will be a 2 by 2. The data pointer will not change, right? The first element of my array will still be at the same place. What about the strides? What will happen to my strides? In order to go from 10 to 13, in the original buffer is the same as going from 0 to 3 here. I still have to jump over 1, 2, 3 like this. So in order to go one row down, I still have to jump over 24 bytes. But to go from one column to the other, to go from 10 to 12, now I have to jump over 2 different things. So I have to jump over 16 bytes. right? So any operation that is expressed as a slice can be expressed, computed basically as a change in shape, a change in strides, and also an optional change in data pointer. So that's why every time you make a slice, you're getting a view into the data, right? Python can say, oh, the data is still the same. I'm just going to use a different offset. I'm going to change your jumps basically, but into the same memory representation. Now, this falls apart if we're doing some fancy indexing. Let's say these 3 elements here, 10, 11, 14. If I do that, there's no way for me to represent that as strides and shape, right? Because from 10 to 11, I've got 8 bytes, but then from 11 to 14, I have 32 different bytes. So whenever you use fancy indexing, Python will actually, NumPy will like give up, be like, okay, you're doing fancy indexing, I'm going to take that data and I'm going to create a new array. And in this case, the 2 arrays will be the same both in the memory world and in the Python world. So another consequence of this representation is that any operation that's done to the shape only is basically free. So NumPy has this concept of reshaping, which is both a function and a method, and you can also assign to the attribute. So if you start off with an array here that has 6 elements, if I reshape it to make it a 2 by 3, what I'm doing underneath the covers is changing the shape, obviously, but also changing the strides. But that doesn't require any memory copy whatsoever, right? Because it can be expressed just like we did here with the transpose or with the slice as a change in the metadata. Same thing with the transpose. This slide is super busy. It has little drawings here of basically what I drew on the board of how it's just swapping the strides and swapping the shape, but transposing is a very cheap operation. The only requirement when reshaping an array is that the total number of elements shouldn't change. So if I have a 2 by 3 here, I can reshape it to be a 3 by 2. That's not a problem, still 6 elements. But if I try to reshape it with fewer or more elements, you're going to get a value error saying the total size cannot change. So you can reshape using the method. You can also assign to the shape, which is nice in a way because it's a single statement instead of doing, I don't know, a equals a.reshape. There's no reason why you would use one versus the other than preference. It's not that one is faster or anything. And finally, there's one particular kind of reshape that's kind of a special case, which is to take your multi-dimensional array and turn it into a flat one-dimensional array. And NumPy provides you 2 ways of doing this. One called flatten, which does always the same thing. It takes all your array, turns it into a one-dimensional array, makes a copy, and gives that to you. So it's a safe copy in a way, but it's also kind of expensive because it requires a memory copy. Versus this other method called ravel, which will return a view if possible. If not, will return a copy. And what we mean by is possible is that all of the elements in the array are next to each other row-wise. So in some of the arrays that I've drawn here, my original array in the middle, down here, I could ravel it. Because 10 is next to 11, is next to 12, is next to 13, is next to 14, is next to 15. But once I've transposed it in the upper right, that ravel is going to give me a copy because 10 is not next to 13 and 11 is not next to 14. So that will give me a copy. It's the difference between the two is the source of like sometimes some strange bugs and also performance issues. So it's good to know about both. And with that, I have a big SciPy logo. There are a few more exercises that we've not done. In the folder, there's one called Dow selection, which is a mix of plotting and fancy indexing. I encourage you to do it. It's really nice. It's just like 4 or 5 lines of code, but it's a really sort of powerful exercise. And otherwise, I hope you had a good time, that you learned a thing or two, and that you will remember a thing or two. So, thank you.